Welcome to this brief video on the evaluation of GreEN and GreEN-like conductive polymers using combinatorially formulated inkjet printed thin films. Our thin film evaluation experiments consist of the process design, which includes identification of factors affecting thin film performance, material assessment, and choice of thin film library preparation methodology. This is followed by material formulation at variable compositions, setting library size specifications, and subsequent library preparation, which is achieved using our combinatorial printing platform. Next, we characterize the prepared thin film library to obtain qualitative understanding as well as quantifiable insights into the specific thin film properties being probed. And finally, the conclusions are analyzed to provide direction to future printing iterations and possibly improve upon existing models. In the rest of this video, we take a closer look at these steps and what each of them involve. In this step, we make the choice of investigating ink composition and thin film morphology, as they are the most critical parameters influencing conductivity response, which is at the center of our experimental goals. In addition, we also assess the functional compatibility of GreEN and GreEN-like conductive polymer dispersions with our printing platform by characterizing relevant ink properties. After we've determined our factors of interest and established ink printability, the next step is to print the thin film libraries. In our case, they can be arrays of different sizes and on different substrates. Our combinatorial printing platform does much of the heavy lifting in terms of ink formulation and film patterning, and provides us with multiple replicates of multiple print variants for testing. Multiple testing methods are employed to evaluate the conductivity performance of the printed libraries. Electrical probing and film profiling can provide useful information on film conductivity and optimal ranges of application. Furthermore, morphological characteristics can be evaluated using optical and atomic force microscopy to understand how they affect film conductivity. Conclusions drawn from this evaluation cycle inform the planning of the next iteration, if needed, where focus is directed more towards ink composition domains, which can potentially optimize film morphology, thereby enhancing conductivity performance. Subsequent tests to study the temperature dependence of conductivity of such optimized thin films can then be conducted and rendered into empirical models.